Christian Bible experiences begin with the Book of Genesis and its famous opening words, "In the beginning." The dogs and I decided it made sense for us too to begin our YouTube experience with this, our inaugural video, the Book of Diagenesis. Diagenesis is the word that describes the group of processes that change sediments into sedimentary rocks. Diagenical changes start as soon as the sediment has been deposited. As the sediments are buried to deeper depths, they are exposed to pressures and temperatures very different from the pressures and temperatures in their original environments of deposition at Earth's surface. The dogs and I have quite a story queued up for you today. Chapter 1 of the Book of Diagenesis will outline just how mud gets changed from soft, wet, clingy mud to solid mudstone rock. We will start with the Bible and mudstones, but because there's no mention of mud or mudstone in the Bible's Book of Genesis, that first section will be pretty short. The raw material for mudstone is mud, so we have to talk a lot about mud and where to find it. Then we'll learn way too much about diagenesis, and finally the dogs will show you what mudstone looks like and where to find that. We've purposefully titled this video, The Book of Diagenesis, so the next time your church leaders and pastors mention the Book of Genesis, you'll smile quietly and think of the dogs. We have a lot of ground to cover on this muddy topic. So much so that the dogs decided to split this into chapters 1 and 2 of the Book of Diagenesis. Because geologists have a pretty good handle on formation of sediments and sedimentary rocks, we were able to make up our crash course in mudstone sedimentology, thus Diagenesis Chapter 1. After viewing Chapter 1, we'll all be singing from the same sheet of music when we take a deep dive into what Auntie Gotzik Gibbon has dubbed the mud problem. That's Diagenesis Chapter 2. At the end of Chapter 1, we will pose a number of questions to the Young Earth Creationist community that will show Bible geologists what types of information conventional geologists need in order to assess the Young Earth Creationists' flood model. It's an inspiring story that we think you'll enjoy. Without further ado, show us what the dogs have dug up for us. Number 1.
The first book of Moses, Genesis chapter 1, starts with the famous line, "In the beginning," and goes on from there to describe in no especially deep detail how God created earth and everything else. Genesis, not a difficult word, only means origin. Genesis, capital G, is an important term to young earth creationists who seem to think they own the word. But did you know Genesis, small g, is also a geology term? In the geology world, Genesis refers to the origin and evolution
Don't say that word.
of rocks, minerals, gems, and other things based on field and textural observations allied with laboratory analyses and experimental studies. And here you always thought Genesis was just a Bible word. Genesis, small g, only means origin in the world outside of Sunday church services and Bible study. It's not a magical word reserved only for the devout. Geologists use the word too. Diagenesis, on the other hand, is the name given to the chemical, physical, and biological changes that occur during conversion of sediments into sedimentary rocks.
I always thought Diagenesis was one of those little-known books not included in the New Testament, number 1.
No, number 2. Genesis is the opening book in the Jewish and Christian Bibles. Diagenesis is the opening video of our YouTube channel. Interesting that Genesis does not mention mud or rocks at all, not even a single time. Chapter 2, verse 7 does say, "The Lord God formed man from the dust of the earth." So dust is mentioned. When dust gets wet, we call it mud. On Adam's birthday, Genesis 2 verses 6 and 7 says it was a misty morning, so there was water available that day. I don't think God spit to make the dust into mud, but we don't know that. God must have made Adam out of dust and mud. Wait, that means Adam was a golem, a mud man. Know what else is made out of dust? Mudstone. So if mud and mudstone aren't mentioned in the Bible, why are we here even discussing? While true that Genesis does not mention mud or mudstones, Bible geologists, and that is a real term, claim that their God created the universe and everything in it. That includes mud. That is why we are discussing it today. We also want to illustrate the conflict between conventional geology and the Young Earth Creationists' Bible geology. Young Earth fundamentalists claim that most of Earth's oldest sediments were deposited during Noah's flood, a year-long event about 4,400 years ago. That was step 1. Step 2 requires all the diagenesis and all the lithification of almost all of Earth's mudstones to happen during that 1 year too. Because young Earth fundamentalists need their Bibles to be fully correct, infallible, and unquestionable, they need to find ways to speed up Earth's processes. That's a very long list of time-consuming processes to happen in only the past few thousand years. We call that a pretty tall geologic order. Let's start with the creation narrative here. In the beginning, October 22nd, 4004 BCE, Sunday, 6 p.m., nightfall. That's when the hard work really began for God. Creating a planet like Earth is no easy task, even for the High One himself. Our thanks to the late Archbishop James Ussher for calculating that so exactly. Ussher counted up all the begats and begots in his Bible and arrived at that specific date and time. Such a masterful calculation for 1650. Just so we're clear, the whole young Earth creation world's 6,000-year-old Earth is from calculations that Ussher made in 1650. Nothing more recent, nothing scientific. That said, according to the Book of Genesis, Day 3 started out with God gathering the waters together into one space and allowing dry land to appear. You can see where we've outlined Day 3. The good book does not specify exactly how that happened, but God's followers have left us images of what they think happened. This view of the biblical creation story is dated from around 1400 or 1410 AD and is kept in the J. Paul Getty Museum. That artwork is exquisite. No matter what you think about religion and geology, you have to admit that the artwork is magnificent. Okay, so creating Earth must have started the rock weathering and erosion cycle on Day 3 of creation. That would have been Tuesday night and Wednesday, October 24th and 25th, 4004 BCE. Remember, we're using the Jewish custom of starting each new day at sundown. We infer that rocks have been weathering and eroding ever since then, and that means mud has been generated ever since. Mudstone rocks must have started forming soon after. No, number 2. Narrator was not there on Day 3 to witness it. He just looks that old. There's really not much more to say at this point. The Genesis and geology shelf is pretty bare. Because the Book of Genesis is mum on Earth processes, Bible geologists have to infer and make lots of guesses about how Earth formed, developed, and evolved.
Oh, don't say that word.
We'll explore a few of their extra biblical thoughts later today, but first let's learn all we can about mud and mudstone.
Okay, let's talk about mud. You've all seen it. What is mud? Where does mud come from? Where do we find mud? Let's jump right in. Weathering and erosion of rocks on land and in the water work together to break rocks down to their individual mineral grains and then even smaller. We call those grains sediment. Informally, geologists split up sediments into two groups: fine-grained, cohesive sediment particles like silt and clay, and coarse, cohesionless grains like sand and gravel. The coarser grains typically are deposited upstream, close to the sources. The fine sediment fraction, the silt and clay, is transported farther downstream. Individual silt and clay grains are too small to be seen by eye. Clay particles are tiny, smaller than 4 micrometers, and usually are thin, flat plates like leaves or playing cards. Silt particles are bigger with diameters between 4 and 62 micrometers. Silt grains can be flat and platy, or they can be rounded. To compare, human hairs are usually 50 to 100 micrometers in diameter. So we have grains of rocks and minerals tumbling downstream in rivers, approaching the coast. During transport, the particles and fragments bump and grind with each other in the streambed as they bounce and scrape along, breaking down the rock fragments a little more each time. The longer the trip to the ocean, the more abrasion and the greater chance the mineral grains will be rounded and smaller. Water also sorts the grains by density, size, and shape. Where the water slows, the fine sediments settle out. Chemically unstable minerals will be slowly dissolved in the river water. Chemically resistant and hard mineral grains like quartz will survive the trip chemically unchanged but smaller in size. Micas are soft and will be abraded to oblivion. As weathering, erosion, and transport continue, the size of the particles becomes progressively smaller, they weigh less, and they get easier to move and slower to settle out. The sediments on ocean beaches are sand, usually with a little gravel. But offshore, deeper than about 30 feet, 10 meters, waves can't act on the seabed. Mud above these depths doesn't always settle because wave action does still occasionally reach the seafloor, keeping the mud stirred up, in suspension, and fluid. But deeper below the wave base, on the inner and middle of the continental shelf, the silts and clays can settle through the water column, that's called hemipelagic rain, and accumulate on the bottom to form the seabed right there. In deep water, muds are then covered over with more mud year after year after year. The muds are compressed, forcing water out, making room for more mud. That compression is the beginning of diagenesis. Once buried, sediment grains face increasing pressures and temperatures. So what we're saying is the weathering and erosion of rocks and transport by wind and water form the silt and clay grains. When deposited in water, that's mud. And the mud is the precursor to mudstone.
Know how to determine if a mud is mostly silt or mostly clay?
No, go on.
Just put a pinch between your cheek and gum like this.
Skull with the wintergreen taste. And just a pinch between your cheek and gum is all it takes.
Oh my, that's really revolting. Narrators should stick to narrating. What does that tell you?
If it feels gritty, it's silt. If silky smooth, it's clay.
That's it. All that gross just for that.
Oh yeah.
Sigh. Redirecting back to the subject at hand. So, the raw materials for mudstones are silt and clay-sized particles, and organic stuff like rotting algae and fecal pellets from seabed worms, those kinds of things. Between the individual mud particles, there are pores filled with water. Pores can also be filled with air, or with both, when above water like on riverbanks or on mudflats between the tides. Especially quiet waters can accumulate organic matter in the mud, especially when there's a lot of algae and critters. But regular mud normally only contains a few % natural organic matter because the organics are lighter and easier for the water to move and keep from settling. But under the right conditions, the organic contents of mud can be really high. When lithified, those are the oil shales that provide North America with lots of oil and natural gas when developed with hydraulic fracturing. That's the fracking controversy we used to hear about a few years ago.
This is editing, geocutting in. During editing, we thought that a quick clarifier might help here. What we've been discussing so far is clay-sized mineral grains. Geologists also use the word clay to refer to clay minerals. We clumsily try to distinguish between clay-sized grains and clay-sized minerals. That's size versus composition. Clay mineral grains, like the common clay minerals kaolinite, illite, and chlorite, are all clay-sized. Other minerals like quartz and feldspar are commonly ground down into clay-sized grains. When we talk about clay-sized grains, we also include clay-sized grains of other minerals that are mixed in with the clay minerals. Did that help or hurt? Editing Geo out.
Let's review how the silt and clay grains, that are mud, move around and find a nice place to settle down. We have grains of silt and clay, mud, being carried along in suspension in water. Mud particles can also be transported by wind. We use the sophisticated scientific term, dust, for that. Mud grains that have been eroded and find their way into water typically make the water appear cloudy. That cloudiness is called turbidity. We use field tests to measure turbidity. When the turbidity gets very high, that means the water has a lot of suspended sediment, and lab tests are used to measure that. High concentrations of suspended sediments can form a slurry, which will appear as a plume of muddy water entering some lake or sea. It's kind of a continuum, as the content of suspended mud particles increases. Turbidity in water is a low mud concentration in the parts per thousand or parts per million range. Fluid mud is high turbidity water with suspended sediment concentrations of 50 to 350 kilograms per cubic meter. That's 5 to 35%. When first settled on a seabed, mud is mostly water and can have a water content of 70 to 80%. When firmed up just a bit, firm mud has a water content of 20 to 40%. Under pressure, the mud consolidates and the pore water is driven out. The top surface of the individual mud layers drops with time, especially with continued additions of sediment on top. We can see that and measure it. Recent research indicates that the Mississippi Delta is settling about an inch, 25 millimeters per year. This is freshly deposited mud consolidating, expelling water, and manifests as the mud-water interface settling deeper into the water an inch or so per year.
Flux. Let's talk floc. Flocculation is the ability of clays to clump together and form larger particles. We've covered how mud particles get to where they drop out of suspension and accumulate on the sea floor. Now we need a quick sidetrack to show how settling can be accelerated.
But what is this whatever?
Gravity works its magic on mineral grains. Larger, heavier grains settle because of gravity. But silt and clay grains are so small that they can stay in suspension and get transported far. Under the right conditions, clay grains can clump together and form larger, heavier grains, which settle faster. Look over here. See that dramatic boundary between brown Fraser River water and the blue Pacific Ocean? Where fresh water with mud meets brackish water, the salt ions in the seawater bind to the suspended mud particles, causing the silt and clay grains to stick together. Those clumps are called flocks. The flocked grains are heavier, and they sink to the bottom. A few examples to show you now. The brown color in the water is the mud. So clay grains can be convinced to settle more rapidly if they can be clumped together. This can happen naturally or with a little bit of engineering. What do we need to flocculate clay grains? Gentle mixing with like-minded clay grains is the start. Gently agitating and moving the water that contains suspended clay grains will allow the grains to come close enough to bump and clump together as their electrostatic charges attract each other, so they will stick themselves together to form the flocks. By the time flocks grow to 1/16 inch, 1.5 millimeter, as large as small sand grains, they are big enough to gravity settle out in just a few minutes rather than the days and weeks it takes without the flocculating. Settling is much more rapid than if they had been left alone as single clay grains. As you can see from this clip, adding a little gypsum to a clay water slurry will make the clay grains flock together and settle fast.
Okay, so here I'm putting half a teaspoon of gypsum in here, stirring it up, and then we'll watch this over the next half hour, and what we should see is that this one that just has soil will stay suspended. This one, which has soil and gypsum, is going to start to settle out. Okay, it's been about a half an hour since we stirred this up and let it settle.
A chemical we call alum is usually what we use to flocculate sediment out of drinking water, like this. So, too gentle a flow, and the clay grains will not get close enough to flocculate. Too speedy and violent a flow, and the flocks will be torn apart. Turbid water with lots of suspended clay grains will flocculate better than clear water with only a few clay grains, but there is a limit. Too many clay grains, and the flocks won't settle as fast because they will knock each other around. That's called hindered settling. Clay grains need time to find each other and spend some quality time together before they can flocculate. Togetherness is important if you're a clay grain. Flocculating can also be induced by adding a little something, and flocking has been used since at least Roman times to purify drinking water and clean sewage. How's about a little recreational math? This one will be quick and easy. Flow velocities in water and wastewater treatment plants that employ coagulation and flocculation with a settlement tank typically use water flow velocities of 150 to 300 millimeters per minute or 0.5 feet per minute. 220 millimeters per minute is a pretty common figure. Velocities this slow promote flocculation and minimize hindered settling. Maybe we're missing something, but 300 millimeters per minute, which is about 1 foot per minute or 0.01 miles per hour, 0.018 kilometers per hour, is really, really slow. Not stagnant, mind you, but that is certainly calm water. Sidebar, the finest young Earth fundamentalist minds like to make it sound like they discovered flocculation and that it explains sedimentation rates during Noah's flood. But all conventional geologists worldwide have learned about flocculation in their sedimentology classes for decades. All civil and environmental engineers worldwide have learned about flocculation in their water and wastewater engineering classes. Flocculation has been used to clean water and wastewater for hundreds and thousands of years. There's no flocking mystery to geologists and engineers. We'll focus on flood sedimentation rates in Diagenesis Chapter 2. Remember that patience is a virtue.
Did you know there's a little more to mud settling than just flocculating? Can we use modern technology and observations to sort some of this out? Of course we can! Sedimentologists perform flume experiments to simulate natural conditions and see how mud particles can be carried along with the current and settle. Indiana University's Professor Jürgen Schieber has an oval-shaped flume that allows for continuous motion. Schieber used a range of water flow velocities of 10 to 26 centimeters per second to demonstrate when his rapid mud settlement can occur. He upped that range to 15 to 35 centimeters per second in 2011. Remember those really slow water velocities in water treatment plants from a minute ago? The fast end was 300 millimeters per minute. That's 0.5 centimeters per second. Compare that to Schieber's 15 to 35 centimeters per second, still really slow. But Schieber's work shows that flocculation can occur at much faster speeds than those used in water and wastewater treatment plants. Schieber made some important findings. Flocculation in clays is universal. Silt and clay can be deposited in currents and can migrate with the current as ripples. Ripples deposited over ripples form distinct beds. Compaction compacts the ripples, making them very thin. The flume is a great example of using lab tests to explain what we find in the natural world. Schieber says, quote, swiftly moving currents can deposit clays, not just from slow-moving or still suspensions. With deference to Professor Schieber, his fastest flow of 35 centimeters per second, 1.1 feet per second, 3/4 of a mile per hour, or 1.3 kilometers per hour, is decidedly not swift. But his overall points are well taken. Links to his movies are in the description. Schieber's experiments demonstrated that mud does not always just rain straight down, but can be deposited by currents. His flume experiments indicate that clay-sized grains that form floccules can be carried along in currents along the seafloor and be deposited in similar fashion to grains as large as fine to medium sand. Clay grains can be transported at faster speeds with faster currents, but only to a point. In ocean waters deeper than a few hundred feet or meters, current velocity can be really slow. The University of Google reported to us that offshore, the Gulf Stream can be 5 or 6 miles per hour, 9 kilometers per hour at the ocean surface, and 4 miles per hour on average, 6.4 kilometers per hour for our Canadian viewer. Easily found measurements of ocean bottom currents seem to be few and far between. But from a quick web search, plus Godin and others in 2024, it looks like currents at the deep sea floor were in a range of like 1.3 to 3.6 feet per second, or 40 to 110 centimeters per second, at depths of a few thousand feet or couple of kilometers. Remember that Schieber's flume tests were running at 10 to 35 centimeters per second, so the flume current speeds were the same order of magnitude as abyssal plane currents. Converting Schieber's numbers into useful units gives us current speeds of 0.2 to 0.8 miles per hour. That's a painfully slow walking speed, and way too slow for a dog. But what does all this mean? The muds that will become mudstone were traditionally thought to have been deposited mostly from settling of the individual grains by gravity in low-energy environments. That hemipelagic rain we touched on a couple of minutes ago, here's where conflict begins anew. Young Earth Creationists think clay grains settling in water currents of 0.2 to 0.8 miles per hour, around a kilometer per hour, is somehow revolutionary.
Okay, I'd like to start this morning session talking to you about flood sedimentation, but I'll give the title of the lecture, Understanding the Mud Rock Revolution. And the Mud Rock Revolution and its relationship to the global flood is described in Scripture. And what I'm going to do is, as a symbol of a revolutionary, what I should do is wear one of those tri-pronged hats, maybe one of those wigs, maybe a little bit of machine gun ammunition over the shoulder or something like that. How should I appear as a revolutionary? Okay, but anyway, I'm leading a revolution, and that's what I tell my students. I'm leading the Mud Rock Revolution.
Holy Hannah, man. It's called a tricorn hat. And that's called a bandolier. How do you not know these words?
Turn it off, number 2. I can't take it anymore.
The dogs and I suffered through the full hour plus of this Mud Rocks Revolution drivel, so you won't have to. But we'd sure like that time back. Dr. Austin's video was painful to watch. Good graphics, but his on-air presence and delivery are just awful. We can accurately report that Austin continues to misrepresent modern geology and embellish the young Earth position based on misinterpreting other geologists' findings. No basis for some kind of mud rock revolution. We're sorry to burst Dr. Austin's mud bubble. Let's return to today's subject, shall we? What we now know is that current velocities in the 0.3 to 1.1 feet per second range, or 0.2 to 0.8 miles per hour, 10 to 35 centimeters per second, did not prevent flocks from forming or tear flocks apart, and the flocks did settle into thin laminae, commonly with microscale ripples. That velocity range is really slow, and we see that the requirement for calm water is still very true. Young Earth Creationists claim that Schieber's discovery has turned sedimentology on its head. Maybe we missed something in our research. Sedimentologists have taken Schieber's results seriously and have done some rethinking. Now we know that mud, especially when flocculated, can indeed be moved along by slow currents, and substantial amounts of mud can be deposited in more energetic conditions than we were taught back in college. Flocculation is probably the key, making the grains large enough to settle more rapidly than we used to think, and in currents moving faster than we used to think. But revolutionary and paradigm shifting? We think not. As far as we can tell, no geologists have ever disputed slow mud speed transport and deposition. Much of what is new here is new now, because of using that flume and observing the micro ripples under the microscope. Same old story. Science advances. Religion reverses.
Okay, now we know that mud is silt and clay and organic matter, and that mud is transported as suspended load and as flocks in the bedload, and that mud can be deposited in calm, quiet, but not necessarily stagnant water. We're almost ready to dive in and see how mud becomes mudstone. But first, let's take a trip around the world and look at where all the fresh mud is. Where do we find mud? Everywhere. Where has a couple of different meanings for us here today: geologically, depositional environments, and where geographically. We'll look at both in turn now. Geologically, silt and clay grains are carried in suspension in rivers and streams into deep lakes and to the open sea. Look for places where the water is relatively calm and quiet enough to let the grains settle out of suspension with or without the benefits of flocculation. That would be deep lakes, mudflats, estuaries, lagoons, and the continental shelves, continental slopes and rises, and abyssal plains of the oceans. Stagnant water helps, yes, but the water does not have to have a zero velocity, just real slow like we figured out a few minutes ago. Remember, some water motion does not automatically prevent silt and clay from being deposited. There is no mystery here. These are some of our favorite drawings to illustrate the depositional environments of mud. See the continental shelves offshore? Lots of mud being deposited out there. Most of the mud we're talking about is only a few feet or couple of meters deep. Out on the open seas, only scientists really care. But when it's a harbor or shipping channel, that's enough to keep the U.S. Army Corps of Engineers and an army of dredging contractors terribly busy.
Where around the world, now, is all the mud that will later become mudstone? Where is mud being deposited now? Look for those places on Earth that fit the descriptions of the geologic locations we just ran through. Most of the world's mud deposited in lakes and on seafloors is delivered by rivers. So you can see that most mud in the world seems to be off of our coastlines. It's right there, coming down the rivers to the sea. First of all, a quick disclaimer. This is not a mud map. It's a sediment thickness map. All sediments, not just mud. Closer to shore, more sand. Farther offshore, nothing but mud. We can see that most of the world's sediments are in the Gulf of Mexico, off the USA and Canada eastern seaboard, off Buenos Aires, and offshore of Asia's Ganges and Brahmaputra rivers. You can see those white boxes at China, too. Either no data in those areas or else China is embarrassed by the amounts of mud they are allowing to form there. The list goes on. Submarine fans offshore of large rivers with large volume discharges of water and sediment. Look off the Po, the Rhone, Rio de la Plata, the Amazon, and the Yellow River. Then look for the open oceans far from land. Once the mud has settled to the sea floor, it requires bottom currents to spread it across the continental shelves and slopes. And way out, the abyssal plains themselves have brown or red-colored clay particles transported by the wind that sink very slowly through the water column. Much of the clay on the Atlantic abyssal plain is dust blown in from the Sahara Desert. Lest we forget what we're looking into. It's mud. It's not mudstone yet. There's still much more work to be done.
Okay, we've seen and heard enough about mud. We've finally arrived. Let's talk diagenesis. Wardens and Burley, 2003, on page 4 say, in the broadest sense, diagenesis can be considered as everything that contributes to making a sediment into a sedimentary rock, from its deposition and weathering at and near the surface through to metamorphism at deep burial. Translating that into the King's English, diagenesis is the suite of physical, chemical, and biological processes that affect sediments following their deposition. Diagenetic reactions include weathering in the open air, oxidation in the water column, consolidation of muds, and lithification. Diagenesis grades in a continuum to all the way to metamorphism. We can see that lithification is just one of a bunch of diagenetical processes that affect sediments in their journey from being raw sediments to being transformed into sedimentary rocks. Let's define a few diagenetic terms, shall we? For mudstones, diagenesis begins once the mud has been deposited. Much too much for me to read there, so allow me to summarize quickly. Compression is the force or pressure that acts on a soil or a sediment being squeezed into a smaller space and volume when acted on by an external load. Can be fast, can be slow, can be natural, can be man-made. Consolidation is an engineering term used to describe the time-dependent settlement of soils and sediments that results from water being expelled from the mud's pores during compaction. The grains rearrange themselves under pressure and push the water out, and that reduces the void spaces and the overall volume. A slow to very slow process because it depends on water being expelled from low permeability materials, which is going to be slow. Compaction is another type of compression where air is expelled from a soil's or sediment's pores by application of a force or pressure, which pushes the individual sediment grains closer together, densifying the sediment as the air is expelled. Volume, porosity, and permeability are all reduced. A geologist's compaction is an engineer's consolidation. Kinda sorta. Cementation occurs when pore waters dissolve grains of the soil or sediment. The dissolved elements then recrystallize into new mineral grains. Cementation reduces the sediment's porosity, increases the density, and increases the strength. Iron oxide and clay minerals precipitated in the pores are common cements in mudstones. Diagenetic processes operate continuously as the ambient temperature, pressure, and chemistry evolve
Don't say that word.
during the deposition, burial, and uplifting cycles that occur during a sediment's history. Diagenetic reactions change the original sedimentary minerals and pore waters, which react to reach textural and geochemical equilibrium with their environment through time. As the conditions change, new equilibria are established and the process continues. So why do we have diagenesis? Wardens and Burley, 2003, on page 4 say that the fundamental driving mechanisms for diagenesis are changes in the pore fluid chemistry and higher temperatures and pressures as the sediments sink to deeper levels of Earth's crust. When first settled down, the mud particles are in direct contact with each other in a skeleton framework. The starting porosity and water content of freshly settled mud can be as high as 70 or 80%. In the earliest stages of diagenesis, new mud settles on top of already settled mud. The dead weight of the additional mud deposited on top compresses the older mud and squeezes out some of the water. This is consolidation, which continues to its endpoint, which is called full or 100% consolidation. At full consolidation, all the pore water will have been expelled. Then and only then can the other diagenetic changes go on. But we have to get rid of all that water first, before any other diagenetic changes can proceed. Diagenesis really picks up steam by the time the mud has reached full consolidation. We can see that volume and porosity decrease with depth of burial. Porosity can drop to 20 or 25% by the time the mud has been drawn down to 7,000 feet of burial. That's 1¼ mile or 2 kilometers. Density, strength, and seismic wave velocity increase with depth of burial. Compression from overlying sediments is how it all begins, by smushing the grains close together. If some of the grains are deformable, that will help. But to really make a mudstone, compression alone won't fit the bill. The mineral grains have to be cemented together. Water is key. Why can't the water draining happen instantaneously? Expelling water from the pores of the mud takes time. Let's look at that a little bit. How much time depends on the permeability of the mud and where it is in its compaction and consolidation journey. Fluid mud is initially mostly water, which drains fast and easily. As fluid mud consolidates to firmer mud, it undergoes at least some consolidation to form a cohesive bed on the bottom. After that, drainage of the pore water is controlled by the mud's permeability, which is notoriously low and slow. Our textbooks all say that we can expect permeability of silt and clay to be 10 to the -5 to 10 to the -10 centimeters per second. For comparison, a typical clean sand has a permeability of 10 to 10 to the -3 centimeters per second, so water drains from sand much faster than water drains from mud under the same pressures. That's why consolidation of mud takes time. Water does not flow fast through consolidating mud. Where sediment deposition is fast, pore water cannot easily escape and the fluids in the mud will be overpressured. So rapid sedimentation slows the pore water moving and raises fluid pressures. This is also a control on migration of other pore fluids like petroleum and methane. Interbedded sands help speed up drainage, but many mudstones don't have any sand beds. As the sediments are drawn deeper, 100% consolidation has been achieved, the pressure and temperature get higher and diagenetic changes really begin to happen. Like geochemical reactions plus more compression and more lithifying. By the time sediments get down to 3,200 or 3,300 feet, 1 kilometer, where the temperature is almost 400 degrees Fahrenheit, 200 degrees centigrade, the minerals in the sediment will have begun to partially dissolve into the deep groundwater. The dissolved ions precipitate out as cement, which are usually calcium carbonate, silica, or clay minerals, depending on what rocks are around and what can be dissolved. Silica and clay minerals are the usual cements we find holding together our mudstones. Any burial deeper than a few miles or kilometers will get us into low-grade metamorphism with temperatures around 400 degrees Fahrenheit, 200 degrees Celsius. We're not sinking our mudstones that far. Remember our talk about permeability a couple of minutes ago? The deeper the sediments are drawn, the more the porosity and permeability are reduced, first by grains shifting around to fill the pores and then by cements being precipitated and clogging up the pores even more. Permeability decreases dramatically from really slow to really, really slow, and that means it will take even longer for the fluids that precipitate the cements to migrate through the remaining pores. With continued diagenesis, the mudstone gets more and more cement until theoretically the primary intergranular porosity is all gone. 0%. Late diagenesis is at depths below about a mile, 1.5 kilometers, and temperatures of 120 to 575 degrees Fahrenheit, 50 to 300 degrees Celsius. Just a little more heat or pressure or both will start metamorphic reactions. We geologists are pretty simple-minded. Couple of simple geology rules of thumb are: diagenesis results in sedimentary rocks. Metamorphism results in metamorphic rocks. Metamorphism destroys the original sedimentary fabric and changes the mineral grains, diagenesis does not. Keep it simple. And with that, we will stop our diagenesis tour. And finally, an end result. We have mudstone. A couple of key points now. We find hundreds and thousands of feet of mudstone around the world. For these thick mudstones to form, we need the original mud to be even thicker. Given enough time, pressure, and temperature, even thick deposits of mud will undergo diagenesis and be lithified into mudstone. For mudstones that are hundreds and thousands of feet or meters thick, we need mud deposits that are thousands of feet or meters thick. The best documented thick mudstones, like the Barnett, Bright Angel, Bakken, and Niobrara, all had to have had subsiding basins and big sediment sources. More on that in a few minutes.
What is mudstone? It's a family of rocks formed of sediments that were initially silt and clay grains. Classifications do differ, but the common threads to the mudstone family seem to be: siltstone has greater than half silt-sized grains. Claystone has more than 50% clay-sized grains. Mudstone is a mixture of silt and clay-sized grains and is not fissile. It's not laminated. Shale is a fissile-laminated mudstone. Argillite is a mudstone that has undergone just a little low-grade metamorphism. Slate was a mudstone, but had just a bit too much temperature to keep it in the mudstone category. Mudstones make up something like 2/3 of all the sedimentary rocks on Earth, so their formation, their genesis, is pretty important.
A few mudstones from the dog's personal collection. Top row are from Montana. Bottom right are from Colorado. And the bottom left, more from Montana. The dogs get around. What else do we see? Little trilobite right in the middle. And his cousin right here on the other side. Beautiful horizontal bedding right there on this one. Up on the top, mud cracks. Remember the colors. We'll see those some more in a minute or two. The grays are typically deep sea floor. The reds, continental floodplains and places like that. And the browns are somewhere in between. They can be continental, or they can also be near shore. Not as deep as the deep sea floor gray samples, but on the near shore sea floor.
We have another live sample of mudstone here. Look at those fine details. That's really not as clear as it should be.
What the? Did you really just lick that rock? We're dogs, and even we think that's gross.
What? That's a sophisticated geologist thing. See how much clearer those laminae and soft sediment deformation features look?
Yeah, you just keep telling yourself that.
Soft, wet plastic muds readily deform under smaller shear stresses before they have lithified. You can see that happened while the mud was still mud. Right there.
Yeah, anyway, after suffering through all those diagenetic changes, mud is lithified, and then we can legally call it mudstone. Yay! Just looking at mudstones gives us more good clues to their formation. Oxidation, or rusting, is the shallowest of the diagenetic changes. In continental environments, mud deposition in water can be followed by long periods of time spent above water, above the river or groundwater. This allows organic matter to be oxidized and removed from the mud. Iron can be originally crystallized in a rock as magnetite or precipitated out as limonite. Both are dehydrated to hematite. It's the hematite that makes red beds red. In subaqueous environments without oxygen, sulfate-reducing bacteria are usually active. Sulfur in the sediments can react with iron to form pyrite, which is really common in black shales. Organic matter can react with sulfate to form hydrogen sulfide gas. Other bacteria present in mud can ferment organic matter during shallow burial, which can generate carbon dioxide and methane. Sometimes, sandstone dikes cut vertically through mudstone. The dikes can be contorted because the mud is compacted much more than the sand is. Conventional geologists call these features clastic dikes, and they form during early stages of diagenesis when the mud and sand were still mud and sand.
New topic. Where is all the mudstone in the world? Studying depositional environments is what geologists do to unravel Earth's history. Wherever we see mudstone on the North America map, for example, those mudstones used to be mud, and the mud was deposited in one of those environments that we just went over. Let's run through just a handful to refresh our memories. Bright Angel Shale, shallow marine; Chattanooga Shale, seabed, possibly lagoon; Marcellus, deep marine anoxic; Antrim, deep seafloor anoxic; Bakken, seafloor anoxic; Barnett, seafloor anoxic; Mancos, offshore marine. This table is only a bare minimum of worldwide mudstone formations. There are way too many others to count. Look at those crazy mudstone thicknesses. Before you go gaga over these formation thicknesses, remember that mud originally with at least 50% porosity will have compressed to almost zero out that porosity. If we double those thicknesses, assuming an initial 50% porosity and a final primary porosity of 0%, the 350 feet, 100 meters, of Bright Angel Shale could well have been formed from 700 to 1,000 feet, 200 to 300 meters of mud. Now you can go gaga. Conclusion. Thick deposits of mudstone require much thicker deposits of mud, and thick accumulations of mud require a couple of things: steady supply of sediment, vertical space to fit all the mud in, and modes of transport from source to depot center. That's a new word. We learned a few minutes ago that thick sequences of sediments, including mud, require space to fill. How do we get thick mud that gets lithified into thick mudstone? How are the sediments drawn down into Earth to reach the temperatures and pressures needed so they get lithified? Tectonic forces drag our continents all over Earth's surface. The dragging and the drifting changes Earth's topography, pushing up here, pulling down there, squeezing and squishing the crust over there. Some of these movements form basins, lower elevation parts of Earth's crust. Many basins start to slowly sink deeper into Earth's crust due to the weight of the sediments being deposited. Some sedimentary basins are formed by faults, so the basin can sink along those faults as sediments are being deposited. Some basins are formed because a tectonic plate is being subducted. Some basins are just pushed up or pushed down or both. Tectonic forces control Earth's history. The motions of Earth's crust brings the muddy sediments down deeper into the crust, where the pressures and temperatures are high enough to lithify the sediments. If the tectonic forces so choose, the sediments, now lithified into sedimentary rocks, will be returned to the surface, where we can see them and learn about their journey. If a different pathway is in the cards, the sedimentary rocks will be drawn even deeper into Earth's crust. Where sedimentary rocks continue their journey to deeper levels, the pressure from overlying rock is very high and the surroundings get really hot. The mineral grains themselves change, and the original sedimentary fabric layering and stratification and such is destroyed. This is metamorphism. We say the sedimentary rocks have been metamorphosed into metamorphic rocks. Back to the basins. Look at those beautiful full color maps. You can see the basins in color. Look at Michigan for one basin. Look at Illinois for another. The Gulf of Mexico is also a basin that is slowly subsiding. Look at the sediment thickness map again. The thickest sediments are shown in reds and yellows. Those are the continental shelves, abyssal plains, and subsiding basins near the continents. At some future time, that's where Earth's future thick mudstone deposits will be. Okay, now, up to this point, conventional geologists and Bible geologists more or less largely agree. From here, however, the two opposing views have little common ground.
This video is already way too long. The dogs overruled me and decided to call it a day. They have such short attention spans. Chapter 2 of the Book of Diagenesis will take up where we left off and concentrate on the Young Earth Creationists' mud problem. We'll post the two chapters up together in a playlist as a special 2-volume collector's edition. Our apologies for the almost abrupt ending. As we were writing up this video, we learned of a paper by Scott Dunn in Creative Results Society Quarterly. It was behind a paywall for a very long time, and we just caught up with it last month.
Did you actually just say Creative Results Society?
Whoops, I did it again, didn't I? I meant to correctly cite them as Creation Research Society Quarterly. Sorry about that. I make that mistake sometimes. Old man moment. The dogs and I expect to look into Mr. Dunn's paper and maybe some other recent publications and videos to prepare Chapter 2 of the Book of Diagenesis. But this is our hobby, not our profession, so we'll need some more time.
What young Earth creationary thoughts and theories do we want to know more about today, number 2? Remember, just Diagenesis Chapter 1 today.
The big board says, 1. We've seen that mud can be flocculated, transported horizontally, and deposited in currents as fast as 1 foot per second, 35 centimeters per second, or 0.78 miles per hour. We have never seen flood mud deposition rates or the velocities at which the flood waves traveled while inundating the world. At what water velocities were the flood deposits deposited? Are young Earth creationist velocities at the time of mud deposition consistent with this newest, flume-based mud deposition scenario? 2. Building off the flume-related research on mud deposition, McAnally and others, 2007, page 1 says that most research indicates that mud is deposited chiefly by somewhat horizontal movements with the current and not by vertical deposition from suspension. Dr. Austin, the leader of the Mudrock Revolution, called for a young Earth flume for their research in about 2007. Does recent young Earth sedimentological research corroborate these findings? 3. Diagenesis of mud into mudstone requires temperature and pressure conditions that can only be achieved a couple of miles below Earth's surface. Under the young Earth flood model, how is the heat and the pressure applied, and what is the source of the heat and the pressure? 4. Lithification of muds into mudstones depends on expelling the pore water during the consolidation phase of diagenesis, which reduces the mud's porosity and permeability. Provide some calculations that demonstrate that mud, using the typical values of porosity and permeability of your choosing, can be lithified into mudstone under a biblical time frame. 5. We've seen that mud can be deposited rapidly in some environments. Rapid deposition prevents pore water from quickly dissipating, and the muds will be overpressured. The young Earth model seems like rapid mud deposition to us. Are the flood muds and mudstones overpressured? How does the flood model of deposition account for muds and mudstones that are not overpressured?
As a science book, the Book of Diagenesis triumphs over the Book of Genesis every time, adding in just the tiniest bit of math, logic, and field observations, and the young Earth fundamentalist position, as with everything they touch, crumbles into the empty void that is their creation myth. Apologies for the last-minute splitting we had to do to keep the video lengths reasonable and manageable. We hope we didn't lose too many of you. And now a few notes to our fellow geologists. Our viewers should recognize that the anti-geology and anti-science world has many adherents that cling to 17th century dogma instead of to modern science. It is incumbent on all of us to resist and repel the anti-science attitude that has been building nationwide and has now reached a fever pitch. A simple plea to my fellow geologists: clean up and tighten up your language. Do not advertise your new discoveries using divisive, incendiary terms like paradigm shifting. This gives young Earth creationists ammunition and allows them to declare that we geologists keep changing our theories, our hypotheses, our inferences. Young Earth creationists use our imprecise geo-language choices to imply that modern geology is clueless about the most basic geological facts. They absolutely do think that way. The dogs and I implore you, tone down your rhetoric. We geologists probably do mix facts with our inferences, stating as fact what are actually our educated guesses. We are perhaps not as strict with our language as we should be. Vague and ambiguous language gives young Earth creation fundamentalists a window of opportunity to demean us and science in general, and muddy the waters of science. They do not shy away from sowing doubt and confusion. That is their superpower. Such wickedness. That's enough sermonizing from us. Thank you very much for watching this video. We are a new channel, so kindly consider subscribing. We dogs need all the help we can get. Tap on the thumbnail for our other videos. We look forward to you seeing us over there.